Welcome to the final 20th lecture of this course, Basic Building Blocks of Microwave Engineering. So, we have seen various signal sources. Now, we will see that we have seen diodes, we have seen tubes that can produce microwave signal. Obviously, people will expect that what about transistors? So, that we will cover that microwave transistors in this final lecture. Now, obviously, compared to small low frequency transistors, a microwave transistors will need to reduce the device and package parasitic reactance, because we have explained that otherwise it will create problem for everything. Also, transit time of the device should be reduced, because since frequency of oscillation microwave region is quite high. So, you need to the transit time of the carriers, they should be reduced much, their transit time should be reduced. Commonly used semiconductors are silicon at this microwave transistors. Also, gallium arsenide is heavily used. So, silicon and gallium arsenide, these are the two technologies from which people make microwave transistors. Now, transit time depends on mobility. So, in gallium arsenide compared to silicon, in gallium arsenide the mobility is higher. That is why for high frequency things gallium arsenide is a superior transistor, gallium arsenide based transistor. Now, fabrication is by molecular beam epitaxy technique, and the transistor where we have high electron mobility, that is called HEMT, high electron mobility transistor, up to 100 gigahertz nowadays you can work or you can get signals from microwave transistors, amplifiers, or you can also use transistor can be easily used as oscillators. Categories of microwave transistors. So, if you want low noise transistors LNA, you can use them. Then if you have low level transistors for driving IF stage, you can use microwave transistors, and for power amplifying signals you can have power transistor for driving power amplifier. Now, you know that microwave ICs, they are of two varieties. One is called microwave integrated circuit or MIC, or another is called MMIC. In MIC, it is a hybrid of various, obviously the active devices are there, but there are also some lumped elements soldered to that thing, and transmission lines are there for signal taking and matching, etc. Not things, not the simple wires, but transmission line concept are used, but still there are some lumped elements, particularly the inductors are lumped. Also, some of the other devices, lumped devices, their resistance, etc. But in monolithic microwave integrated circuits, all active and passive components are fabricated on a single crystal. So, the transmission lines, active devices, passive devices, everything is on a monolithic crystal. That is why the name monolithic microwave integrated circuit. Now, these microwave transistors are used in both of these varieties of ICs, either MIC or MMIC. Now, construction of, you can have bipolar transistors. So, in bipolar transistors we know 3 semiconductor doping region, either PNP or NPN type of variety, and we know that in bipolar both electron and hole are carrier. Silicon BJT in UHF S band is used. These are higher gain, but you can also have unipolar transistors. So, in unipolar 1 or 2 semiconductor doping region, in unipolar there is only one carrier, all like low frequency things, either electron will be carrier or hole will be carrier depending on the channel, etc. Silicon BJT or gas FET, they are of this type. So, S band and C band operations are available. S band is 2 to 4, C band is 4 to 6 gigahertz. Unipolar has obviously better noise performance. We know that because FETs are better and their frequency of operation is higher, only thing their gain is not much like bipolar. So, microwave bipolar transistors, let us see, they are planar in form. This is the structure, this is the array, mostly silicon, up to 5 gigahertz they work. Geometry for monolithic thing, they can be interdigitated, overlay or in matrix forms. So, microwave bipolar transistors from silicon technology. Then beta cutoff frequency is typically 22 gigahertz. So, up to 5 gigahertz they are used, and transit time depends on this. You see the transit time will depend on emitter base junction capacitor charging time, base region transit time, base collector region depletion layer transit time, then base collector junction capacitor charging times. Out of these capacitor charging times, they can be neglected, but this base region transit time and base collector region depletion layer transit time, that means basically you will have to cross the base, and then also there is this large depletion layer here. So, that depletion layer, these two you will have to consider, and so that was about bipolar, but unipolar FET mostly they are made from gas, they are high mobility devices. For microwave frequencies, they use Schottky barrier gate, and that is called MESFET. Also, there is a variety called high electron mobility transistor HEMT. Now, again here the transit time, if you can minimize, you can get much higher beta cutoff frequency FT, but FT you know that they are at FT the gain is 1. So, people do not use at beta cutoff frequency, you want it much lower than that, but up to that theoretically you can have the amplifier. So, MESFET, its gain is typically 10 to 15 dB at 2 gigahertz. Noise figure you see that impaired diodes etc., they were giving 30 dB etc., but here noise figure is less than 1 dB, that is required, because in practical LNA etc., type of application you require 0.3, 0.4 dB of a, more than that is not a. So, this is a MESFET structure, you have source, you have gate, you have drain, and semi insulating gas substrate, energetic shell gaps. So, basically same structure. Then HEMT, you have this special device. So, again source gate drain, but the gas and gain is see 15 dB quite good at 8 gigahertz, but if you go to 50 gigahertz 6 dB, but you see the noise figure 0.4 dB at 8 gigahertz. At 50 gigahertz obviously problem 1.8 dB, but the HEMT, it has a very good noise figure. So, from noise applications etc., or very low noise applications, HEMT is preferred, and it is giving quite good amount of gain. You see 15 dB of gain at 8-10 gigahertz from a transistor, it was unthinkable 10-15 years ago, but now we are having this type of microwave transistors. So, these are some figures we have in our laboratory, this type of packaging. These are MESFET and HEMTs. So, looks like normal transistors, you see this is looks like normal IC, but quite good packaging. And cost wise also, what was the cost of transistors few years ago, these are having same thing. So, nowadays the low frequency things, we cannot now say that okay, microwave people do not have transistors. In your professional life you will see that these microwave transistors will be heavily used instead of other various devices, but for till some time these high frequency, high power applications will be still dominated by tubes, etc. But for low power applications, all will be solid state things. There these other devices won't be there, and we have seen only diode based oscillator, etc. With this microwave transistors, you can get much better oscillators, etc. So, in microwave region, we will see much better stable oscillators with the use of this. I think with that we end this course, where we have mainly seen the various microwave technologies, some building blocks, particularly the transmission side, that how to model the whole transmission system, what are the various key concepts in waves, particularly the mode concept. So, what are the basic modes? Then we have seen that how with the knowledge of that modes you can analyze that how microwave signal propagates to various transmission structures, and then we have seen some passive microwave devices, those are necessary for manipulating the signal transmission, and then we have seen that obviously a transmission system you need some active devices. So, we have seen what are the sources of power which can give you power, which can with their negative resistance or with their some mechanism of gun, etc., or mechanism of some carrier flow of hole or ray, we can produce microwave level microwave frequency signals. So, with that we think you have got a good glimpse of this, but obviously I again remind you that prerequisite to this was a course on another course we had on this NPTEL, that basic tools of microwave engineering, where we have introduced 3 basic tools: the Smith chart, the scattering parameter and signal flow graph. You need to have that knowledge, so that you can utilize that tools to have understanding of these basic blocks, and with this we hope to proceed it further, that other microwave technologies, other facets we will try to introduce in later NPTEL courses. So, I think the concept we tried to make simpler, but if you still feel that you require more understanding, etc., you can contact us. We will be happy to share our knowledge with that. Also, I say that the some of the reading materials we will be uploading, and from that you can gain more insights, particularly the mathematics part we tried to keep minimum, so that you can focus on the understanding concept of physical things, but that mathematics is also required for understanding the technology. So, that you can refer to our notes, we will be uploading them soon. Thank you, enjoy and take this microwave technology as one of your career thing. It is a pleasure, I tell you, that this microwave technology gives lot of pleasure to us. Hope that with this sharing of knowledge, you will be also able to enjoy this technology and change the world. Thank you.